So now to review what we've done in this section on RSA encryption, we first of all noted that it's the basis of almost all internet security and financial transactions. It was discovered in 1977, in fact earlier in 1974 in British intelligence, but that was kept secret until the 1990s. So RSA security relies on the difficulty of factorising a large number n, which is known to be the product of two primes, but the primes are not known. In fact, if you take a number n, which is 232 digits long, this is an example done recently, or perhaps about 7 or 8 years ago, that takes the equivalent of 2,000 years on a single computer, a single reasonably fast computer. However, 232 digits is what you obtain if you take two primes, each about 165 digits or so. So, as computation speed gets faster, then you can, of course, just add some extra digits to the primes p and q. And as a very rough rule of thumb, for each 10 digits you add to n, the amount of time it'll take goes up by a factor of 10. So if you added 300 digits, then the time to factorise would go up by 10 to the 30, which of course is much greater than the lifetime of the universe. So RSA encryption looks reasonably secure for a while to come. Quantum computing, on the other hand, will make a big difference. And also I should note that the calculations actually involved in RSA encryption and decryption only take fractions of a second. That's provided you know a certain exponent, as we'll see in a minute. So the method is as follows. Suppose Bob wants to set up a method whereby people can send him secret messages, or as we've seen before, can send him secret numbers. So what he does is he chooses two primes p and q, each 150, say 300 digits long. So it's going to give n, in that case, about 600 digits. And then compute various numbers. N, m, which is p minus 1 times q minus 1. The number e, it has to have a greatest common divisor equal to 1 with m. And then d is chosen to be the multiplicative inverse of e modulo m. Now the public key, the key that Bob publishes, whereby anybody can send him a private message, a private number, is n and e. The private key that Bob and only Bob knows is the number d. Bob also uses n when he does decryption. So now, if Alice wishes to send Bob a secret number, she takes the secret number w and then raises w to the power e modulo n, and then publishes the number c. And then Bob, to decrypt, raises c to the power d. And then by the RSA theorem, which we'll just note again in a minute, w and d are the same. So the RSA theorem, which justifies this, says that if p, q, n, m, e and d are as above, and w, the secret number, is less than n, remember n in our case is about 600 digits, then if we raise w to the power e, which is what happens under encryption, and then raise the result to the power d and take the result modulo n, one will get back w. So that's the RSA theorem, and the key idea behind the proof was, well, if p divided w, here we have p does not divide w, if p does divide w, then both sides here and here are 0 modulo p. On the other hand, if p does not divide w, then we can write w to the power ed, because e and d are multiplicative inverses. That means ed, e multiplied by d, is equal to 1 modulo m. So that means that e multiplied by d is a multiple of m plus 1. So we can write w to the power ed as w to the km plus 1 for some k, for some multiple k of m, to get km. Then we pull the factor w out the front and we end up with w to the km, and km is just k times p minus 1 times q minus 1 because of the result here, the definition here of m. Now, because P does not divide W, by Fermat's little theorem, W to the power P minus 1 is equal to 1 modulo P. So that means that we can rewrite this as this here, K, P minus 1, Q minus 1. Take the K and the Q minus 1, and W to the power P minus 1 is equal to 1 modulo P. So we went through this before, and that gives us this is equal to 1, so this is equal to W. So in other words, W to the ED is equal to W modulo P, congruent modulo P. The P down here just means modulus is taken modulo P. Therefore, P divides W to the ED minus W. By exactly the same argument, Q divides W to the ED minus W. And therefore the product PQ, namely N, remember P is not equal to Q, N must also divide this, which means this is equal to this modulo N, which is what the RSA theorem says.